Hello everyone. Welcome to the video lecture series of Theory of Automata and Formal Languages. So we are into lecture number 1 of unit number 4 and topic is pushdown automata. So here we are going to start off with our unit number 4 with basically we will be concentrating on pushdown automata and how it generally works. Then what is the transition function working on pushdown automata. Then we will also look into how to convert a pushdown automata to a context-free grammar, vice versa. Okay, so basically we will be looking into the context-free languages as well, but that will be later on. But initially we will be starting off with the construction of a pushdown automata. Okay, so this is, I have already given to you a formal description and some PDA graphical notation, वगैरह. But before going into this topic, let me introduce to you why we require pushdown automata, or what is the concept behind pushdown automata. Okay. So before starting off with the concept of pushdown automata, let me introduce to you the hierarchy, or you can say the relationship between context-free grammar, context-free language, then pushdown automata. Okay. So if I tell you about the grammar that we'll be using over this pushdown automata is context-free grammar. Okay, and from the context-free grammar, the language that we'll be taking is your context-free language, correct? And then the acceptor in this particular grammar will be your PDA. That is nothing but your pushdown automata. Now, generally, if you ask about types of pushdown automata, yes, we are also having. That is your DPDA, and the other one is your NPDA. Okay, DPDA stands for deterministic pushdown automata, and NPDA stands for non-deterministic pushdown automata. Now we will, as I have told you, that after completion of conversion of pushdown automata to context-free grammar and vice versa, we will also look into the concept of deterministic context-free language, then the power of DPDA, the power of NPDA. But for the time being, I will let you know that if we talk about both these categories, we will be if we talk about the power of these two, the power of these two is having, NPDA is having a highest power in comparison to DPDA. So generally, for all context-free languages, you can create NPDA. There is no doubt about it. But for only some context-free languages, you will be able to create DPDA. So to keep in mind, okay. So therefore, for this, if you write for some context-free language, you can create DPDA. For this some context-free language, this has been again categorized as DCFL. Okay, the deterministic context-free language. So this regarding this also we will talk later. But finally, this is the general relationship between all these three. So this is the you can say the derivator, or you can say the generator. Okay, and this is the language part, and this is the acceptor part. Okay, so this is a basic introduction. But if I talk about this structure that I have drawn below, this is the one, you can say, a physical diagram of pushdown automata, or geometric diagram of pushdown automata. Okay. Now, if I ask you why pushdown automata is required, already we are having these finite state machines. If we talk about any, as the name suggests, as the name explains, finite machines, that means it works only with the finite number of strings. So suppose if I talk about a language like a to the power n, b to the power n. Now, if I have to represent this or expand this into a string, then a dot 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 b b b dot dot dot. Correct? That means if there is a sequence, right, where after completion of entire A, B generally starts. Okay, now in finite state machines, this concept of memory is not there. What is the concept of memory? Because if you have to accept this kind of strings, then definitely after completion of all the memory of all the A's, these should be stored in a memory, and thereafter it have to retrieve the or read the elements, that is B. So once it is done, then you can merge these two things. That means these A's, all the A's, you need to store in a particular memory. So that's what is not possible in finite state machines. But if we have to introduce, or if we have to accept this kind of languages, we need what? Memory, and that is possible in push-down automata. So basically, if you want to say in simple way, push-down automata is nothing but a combination of finite state machine with a stack memory. That's it. That means a memory is introduced where you can read the first part, you can store, then you can again read the second part. If you want to continue with the third part, then again you can store the second part, and then you can read the third part, and then finally you can accumulate all the strings together. Okay, so this is the general requirement of PDA. Okay, as I have told you that this is nothing but your you can say diagrammatic representation of PDA. Okay, now what is how it is been working, I will let you know. First of all, as this part, if you talk about this part, okay, this is simple as finite state machines, okay, where we are having an input tape. In that particular input tape, the string will be there. Then the finite control machine will read those strings with the help of read header, and then finally it will particularly write or accept the string, okay, once it reaches the final state. So that is the general concept behind finite state machine. But here what it will do, it will read and it will store in the stack, and then again it will read from the top of the stack. So that means insertion and deletion will be done in the stack of the first of whatever repetition is there, and then again it will revert back to the input tape. Okay, now sorry, the output tape. Okay, now this is the general diagrammatic representation of PDA, where the insertion and deletion will be done in the stack. The insertion and deletion will be done in the stack. So that means the stack memory is used as a part of storing a particular sequence of datas. Okay, like suppose, as I've told you, a to the power n and b to the power n. First it will read a and it will store in the stack. Once all the a's are done, then it will start reading b, and then finally it will accumulate a to the power n, b to the power n. Okay, this is how the reading is being done. Okay, now the question, you might have a question like this is actually a question generally being asked. Okay, why stack is used as a data structure as a memory, as we are having other data structures as well. So if you want to know the answer, you can pause a video, and then you can think of it, and you can justify my answers as well. Okay, so what I am thinking is that, what is the use of stack? Basically, stack is said to be a zero address data structure. Why? Suppose if we have to insert or delete in any memory, then we have to allocate the address of the particular location where we will be inserting or deleting from. Okay, that is, indexing is required. Therefore, we have to check overflow and underflow condition as well. But in case of stack data structure, it is known as a zero address data structure. It doesn't require any kind of indexing. That means insertion and deletion can be done from the top of the stack. Therefore, only for this condition where you no need to where you are not having any option of like inserting an element, you are having an option of inserting an element, but you no need to find the location of where you have to insert the element. That kind of data structure is very much easy to carry forward this kind of PDA, because as we are not studying data structure, we are only dealing with theory of automata. We have to consider the easiest data structure that we can use, and the easiest one is nothing but your stack memory. Why? Because stack is said to be a zero address data structure where insertion and deletion can be done from the top of the stack. And once we reach the bottom of the stack, where we will also show you the symbolic representation of the bottom of the stack, where you can find out that yes, we have reached the bottom of the stack. That means everything is done, the operation is done. So that is one more question to you, that why stack is used as a data structure in PDA apart from in comparison to other data structures. Okay, and this is the diagrammatic representation of PDA, where a finite state machine is there which operates, as you have already studied in DFN and FA, with the help of read header through an input tape. Generally in PDA we generally consider an infinite input tape, and we have to reach this input tape. How it works is that read header will start reading from this input string. It will go continue, and once it reach this epsilon symbol, it explains, or it finally says that we have reached the end of the input tape. That means entire string has been read. But during this particular reading operation, if you are having an infinite, if you are having a language like this where A is n number of times A is there, after completion of A, then B starts, then A, after reading all the A's, we have to store one after another into the data structure, and then we have to read all the B's, and then finally we reach epsilon. That means the entire string has been read. So this is the general working procedure of a PDA. Now, in terms of mathematical representation, PDA is represented with the help of 7 tuples. So let me introduce to you the 7 tuples, and then I will explain to you the diagrammatic, you can say a graphical notation of PDA, and with the help of which we will be working on a language. Okay. So as I have already informed, already introduced to you the definition, and this is the mathematical or formal description of a PDA, where we are defined with 7 tuples. Q, then epsilon, sigma, then capital gamma, okay, then delta, then Q naught, Z naught, and F. Okay. Now this Q generally represents a finite set of states. Already you know in DFA the same thing. Then sigma generally represents a finite set of input symbols, correct? Then capital gamma, I have already mentioned over here, a finite stack alphabet. This is new to you, correct? This is new to you. Okay. Delta, already you know the transition function, correct? Q naught is the start state. Z naught is another new symbol for you, that is the start stack symbol. Okay, this will help you to identify that the stack is empty or not, or you can say that the stack is the reading of input string is completed or not. And F, as you already know, is the final set of finals or accepting states. Okay, so these are the 7 tuples that is being used. In some of the books, you might find Z in place of Z naught, delta is used. Okay, so don't get confused. Both are same only. Okay, and okay, so these are the 7 tuples that for pushdown automata. Now here you need to remember this thing. Now this regarding this particular transition function, we will be learning in the next lecture video, where a language will be given to you, and for that language you have to design a pushdown automata based on this transition function. So you just note down the definition right now, but we will be also working on this, or we will be explaining each and every term once we are into lecture number 2. But I will introduce to you what is the structure of this transition function. This transition function consists of 3 parameters. Okay. And these 3 parameters are Q, that is a state of Q. It may be the present state, it may be the next state. So I will let you know with an example. Okay. A is nothing but an input symbol in this one, the finite set of input symbols. Okay. Then A can be epsilon also, that means empty symbol. Okay. And X is a stack symbol, that is a member of gamma. Okay. So these 3 parameters you need to remember. We'll be discussing this in the lecture number 2. Okay. Now, last one, the output of delta, okay, is a finite set of pairs p comma gamma, where p is a new state, gamma is a string of stack alphabet that replaces x at the top of the stack. This also we'll be learning in lecture number 2, because we will be dealing only one example where a language is given to you and you have to construct a PDA based on this transition function. There we will learn this parameter also and the output also. Okay. So okay, for the time being, you just note down the definition. But today in this video, we'll be learning this graphical notation working process. Okay. First, let me introduce to you a difference between finite state machine and pushdown automata, where on the first difference is where memory is not there in finite state machine and PDA is having a memory which is used as a stack. Okay. Now, finite state machine, already you know the diagrammatic representation, initial state and final state, and the transition is there. But here, the same concept will go. Let me mark as a final state, okay? The same concept will go, but the transition will consist of 3 parameters, A, B, and C. Now, this you need to memorize, okay? A, comma, B tends to C. This is a representation. And A generally represents the input symbol that you are reading from the input tape. Okay, it may be epsilon, it may be the input string. Okay, and next B is nothing but the top of the stack, symbol at the top of the stack, and this symbol is to be popped. So you can also remember like input symbol, then popped symbol. Okay, and then finally C implies C. This symbol is pushed onto the stack, so you can also remember as pushed. That means finally I can say that A comma B tends to C. You can remember this in a short form: input, pop, push. Input, pop, push. Okay, this also you can, in this way also you can remember. But we will be discussing with an example now. And you can also, in push, you can also find epsilon. This means that nothing is to be pushed. Okay. Okay, now let us take an example where we will be learning how a language is given to you and you need to draw or you need to construct a PDA. Okay. Let me take an example.